Hi, and welcome to Dr. V's Chemistry webcast. Today we're going to talk about atomic radius trends. It's one of the several periodic trends that chemistry students need to know. Here's what I'd like to accomplish in this webcast. First, of course, we need to state the radius trends, the period trend, and the group trend. You absolutely need to know them, and why these trends occur the way they do. And finally, wrap up with doing some practice problems. These are free response questions that you might see in an honors level first-year chemistry course or maybe an AP chemistry course. If you're not familiar with Coulomb's law, you might want to go and watch that webcast and then come back and listen to the rest of this, because the explanations depend heavily on Coulomb's law, and I would hate for you to be lost when it's a fairly easy fix. So, the periodic law, right, is the basis or the statement that says, hey, we've got periodic trends. When the elements are arranged in order of increasing atomic number, there's a regular and repeating pattern in their physical and chemical properties. So we're talking about atomic sizes. As we go from left to right, we can compare and predict the sizes of the elements. As we go down a column, we can compare and predict the sizes of the elements. That's what the periodic law is basically telling us. So, we're going to focus on atomic radius. Let's talk about what that is. Now, you've learned in geometry class that a radius goes from the center to the edge of a circle, right? So from the nucleus of the atom to the edge of the atom. Well, that sounds all very well and good until you remember that in the modern model of the atom, it's a probability cloud. There is no hard boundary to the edge of the atom. So this isn't really a measurement we can make directly. We need a different tactic. So instead of trying to measure from the nucleus to the edge, what if we tried something different? What if we had two identical atoms bonded together, say a diatomic molecule? We can measure the distances between the nuclei. We could use X-ray diffraction and measure the internuclear distance, which we could call d. And we could assume that half of that distance would be the radius of the individual atoms. Now, we are making an assumption here. We are assuming that the radius when they're bonded together is pretty much the same as the radius would be for the isolated atom. We've got to do something. We can make these measurements. They're meaningful and helpful. So a lot of this data has been collected for us already. It's not like we have to go and do the experiments ourselves. And it's been tabulated. Here's a graphic from Pearson, and it shows the data. So we're going to start with the period trend. As we look from left to right, what you can see is they get smaller. That's the period trend for atomic radius. So, as we go from left to right, atomic radius decreases across the period. So we go from potassium to calcium and so on. It's not a very dramatic trend. It's actually kind of subtle. But why? Why does this occur? You need to know the trend. Absolutely. You need to be able to state that atomic radius decreases left to right. But you need to be able to tell me why. Your teacher's going to want it to. It's not just me. So what you have to remember is that we're adding electrons to the same energy level. All right, and this is very important. So if we think about potassium, it's got that one valence electron in the 4s sublevel. And then calcium, its next door neighbor, has two valence electrons in that same 4s sublevel. So we're adding the electrons to the same energy level as we go across, which means the electrons that are in the atoms aren't repelling each other any more in calcium really than they are in potassium. All right, those electron-electron repulsions, or sometimes it's called the shielding effect, are pretty much the same. But, all right, the other thing we have to remember is that the nuclear charge, the number of protons, is changing as we go from left to right across the period. So if we think about potassium with its 19 protons versus calcium with its 20 protons, all right, this is really the origin of the difference, all right, of that change, all right. What we're seeing is that the 20 protons in calcium hold those valence electrons in the 4s sublevel more tightly. There's a stronger Coulombic attraction than the 19 protons have for potassium. All right, so we have a stronger Coulombic attraction between the nucleus and those outermost electrons as the nuclear charge increases. And this is really what you need to say in terms of explaining the period trend for atomic radius. All right, those outermost electrons are held more tightly, they're pulled in a little bit more, and therefore the radius gets a little smaller. Now, if we look down a column, what we see is that they're getting bigger, right? This is a little more dramatic, this trend. So going down a column, we see a bigger change than we do from left to right, where it's a little more subtle. So again, the atomic radius decreases down a column, but why? Why is this? Well, it comes down to the fact that we're adding additional energy levels, or you may refer to these as shells, as you go down a column, right? So if we go from, lithium to sodium, potassium, we're adding more energy levels, which means the valence electrons are in higher energy levels that are inherently farther from the nucleus. All right. So you have a weaker Coulombic attraction between the nucleus and valence electrons, right? Coulombic attraction Coulomb's law tells us that as distance increases, the strength of the Coulombic attraction decreases. So as they're farther away, inherently, they're going to experience a weaker attraction to the nucleus. All right. And so those outermost electrons aren't held as tightly, and they move a little farther away. All right. It's really important that you understand it's because we have a weaker Coulombic attraction between the nucleus and valence electrons, because the valence electrons are in high energy levels farther from the nucleus. Now, we also do have more shells of electron between the outermost electrons and the nucleus, and that plays a role as well. All right. So we have more occupied shells. There's more core electrons, those inner electrons. All right. And therefore, you have more electron-electron repulsions. You have a greater shielding effect. All right. So the electrons in the 1s sublevel experience some repulsions relative to the 2s sublevel. And so, they're repelling each other. So the more shells you have, the more energy levels you have, the more of these electron-electron repulsions you have between the shells. And so those outermost electrons don't end up experiencing a very strong attraction to the nucleus. All right. The outermost electrons are farther away. There's lots of electron-electron repulsions from those core electrons, and therefore they experience a weaker Coulombic attraction to the nucleus than the electrons that are in inner energy levels. So let's do a practice problem. All right, the atomic radii as several elements are shown in the table below using principles of atomic structure. Explain why strontium has a larger atomic radius than calcium. Now, I'm actually giving you the trend here. I'm giving you the data and showing you atomic radius measurements. Why do they occur? Notice that the question talks about principles of atomic structure. I need to do more than just state the trend here, which I've given you, but I also have to relate it to what atoms are made out of. All right. So we know that calcium atoms have 4 occupied energy levels. Strontium atoms have 5 occupied energy levels. So the outermost electrons in strontium are farther from the nucleus than the outermost electrons of calcium. And therefore, the outermost electrons in strontium experience a weaker Coulombic attraction to the nucleus than the valence electrons of calcium experience to its nucleus. All right. So that's the kind of answer you would need for this question. Let's do another problem. All right. Why does calcium have a larger atomic radius than selenium? All right. So we know that calcium's all the way over on the left in group 2, and selenium's a p block element. All right. So we see that and expect selenium to have a smaller atomic radius. All right. What we need to remember is that both elements have their outermost electrons in energy level 4. All right, selenium atoms have 34 protons compared to 20 protons in calcium. This is really the heart of the matter right here. All right, so the outermost electrons in selenium experience a stronger Coulombic attraction to the nucleus than the valence electrons of calcium. It's all about the nuclear charge. They're both occupying the same energy level for the valence electrons. Okay, so this is what you need to have in an answer like this. Remember, you have to refer back to the atomic structure. Very important. So let's summarize here. You do need to know the trends. Absolutely, you need to memorize these. You need to know that atomic radius increases as you go down a column. Here's a visual that might help you to remember that. Makes me think of snowmen for some reason. And as you go left to right across the period, atomic radius decreases. Another visual. Now, these are not to scale. It's just a visual aid to help you remember the pattern. All right. And Coulombic attractions, being able to relate this in terms of atomic structure is really important. Things to remember when you're writing answers on a test or in a homework problem set. Restating the trend is not an explanation. If I ask you to explain, I want you to be talking about occupied energy levels, nuclear charge, Coulombic attraction. Restating the trend is not enough. That's not going to get you anything. And specify what you mean. Do you mean sodium? Do you mean lithium? Do you mean potassium? Do you mean strontium? Whatever element it is, refer to that element. Write the name in the symbol and be really specific. When you say it, your teacher might not know what you're talking about. So be very specific in your answer. Your answer doesn't have to be lengthy. It can be a few bullet points, but you do need to get to the gist of it, all right? And make sure you've got your atomic structure built in. And if you haven't already done so, make sure you subscribe to my channel. Have a great day. Keep coming back and learning more chemistry with Dr. V.